that they have planets. So how many stars are in our galaxy in the Milky Way? Anybody know? That's very close, yes. Probably maybe 10 billion. So you're only off by one order of magnitude. But yeah, over 1 billion stars, maybe 10 billion stars, or even actually I think it might be 100 billion stars, but that's still very close. So that's a lot of stars. And if each one of those stars has one or more planets, that's a lot of planets. And not only that, but how many galaxies are there in our universe? There's at least 10 billion galaxies with at least 100 billion stars in it. And if each of those has 8 to 12 planets, that's a lot of planets. So it'd be kind of weird to think that this is the only planet in the entire universe that has something alive on it. But we don't know, even though a lot of people think it's very likely that there's life out there somewhere, we haven't found it yet. So we can't really say that we know it because we've never found evidence of it. Now, there's probably life on Mars, and we know that because some of the things that we sent there, NASA didn't sterilize it. And so if there wasn't bacteria there, there probably is now. So we probably brought life to Mars, right? Which is, there's actually 3 possibilities of where life came from on this planet. What are those 3 possibilities? Well, yes. The Big Bang, yeah. That's how we think the universe was created. But how did life get to Earth? Well, one is God created it, so God put it here. It evolved from organic molecules. Or the third possibility is it came from somewhere else. So there's if you watch The Twilight Zone, there's a really good episode of The Twilight Zone where there are these 2 people that crash land on this planet. And in the end, you find out that their names are Adam and Eve, that they both came from spaceships from 2 different planets. So maybe there was another planet out there somewhere where somehow it got to here. Maybe that planet exploded, it had some bacteria on it, and then some of those rocks came here, and then that bacteria turned into all life as we know it. Now, you go to a Catholic university, in case you didn't know that. So having faith and believing in science, those 2 things are not contradictory. And if there seems to be a contradiction, it's just because probably humans aren't smart enough to understand everything. So we as human beings have to get over this Western mindset of everything has to make sense all the time. We can't live with any contradiction because sometimes we don't always understand everything. And so it doesn't matter if not everything makes sense to us right now because maybe we're just not smart enough to understand it. So, but if you're a biologist, you could get a job for NASA looking for life on other planets. I would totally quit my job right now and go work for NASA. No, although NASA would be pretty cool, so I probably would. But all right. So let's talk about 1D motion. So we do need to talk about our good friend Sir Isaac Newton. Later, we will we'll calculate how much a T-Rex must have eaten. Now, how did the homework go for everybody? I got some emails about significant figures. So people were pretty freaked out about significant figures. So I'll go back and look. I'm going to look at everybody's homework. I'll probably do it at the same time. And I'll check to see if you missed a bunch of points for significant figures. And if you did, I can see you shouldn't have gotten the whole problem wrong, but I'll check on that, okay? How many people had problems with significant figures? All right, well, I will go back and look at it. Did you miss the whole, did you lose all the points or just some of them? How much did you lose? Okay. So how bad did you mess up the significant figures? Oh, only one? Oh, okay. Well, all right. Well, I'll go back and take a look at it. All right. So let's talk about linear motion. And in the context of living organisms, motion is often important because that is usually, predators have to catch their prey, and you can't have a healthy ecosystem with predators. So one of the questions is, well, how fast could a T-Rex run, right? Because T-Rexes were really big. They weighed, I think it was maybe 24 tons or more. And so the question is, well, if their bones were made out of the same things that are similar to modern lizards, would their bones be able to support that kind of weight? Right? So we'll think about that later, but so uniform motion means that if I took a stop picture diagram, meaning if I took a picture every 1 second, then so between each of those pictures of the guy on the thing, there's about the same amount of distance, and he's not turning, and so that is what we call uniform motion. So he's not accelerating at all. He appears to be traveling at a constant velocity, and so that's what we call uniform motion. He's not accelerating, and there aren't really any significant forces acting on him. So we're going to treat that, we're going to call it uniform motion. So cheetahs are capable of very high speeds, but more importantly, it's capable of a rapid change in speed called acceleration. They can go from 0 to 70 miles an hour in about 3 steps, okay? So they accelerate very, very quickly. And that's how they get their prey. Now, a cheetah doesn't have the metabolism to maintain that speed for very long. And so it's very important that he catches prey in that amount of time. And the cheetah can only run like that for about 2 seconds, and then it basically overheats because it's metabolizing so much energy that it's just not possible. But it has evolved to give it this burst, I guess, of ATP, and so it can run very quickly. So it has to catch its prey really quickly, and it also has to have a tremendous amount of friction. So friction is also very important for many living organisms. So you want to have low wind resistance, probably. So its head looks very aerodynamic, and it also has very high friction on its feet to grip the ground. Okay? So friction and drag, very important, especially for sea creatures. Whales are very aerodynamic. So, and that's important for when they're alive. Okay? So when they're hunting and traveling great distances, they need to be very aerodynamic to save energy so that they can survive. So when a diver jumps, his motion, both going up and coming down, is determined by gravity alone. We call this free fall. So if you jump off a cliff, you're falling down. So when a hawk is hunting, it puts its wings in beside its body. It makes its profile very small, and then it falls straight down, and it gets accelerated by gravity. So a hawk will use gravity to hunt its prey, just like an eagle too. An eagle does the same thing. The eagle has obviously really good vision, and when it sees its prey, it uses gravity to accelerate very quickly. And so it uses almost no energy, and it can attack its prey like that. All right. So we can analyze motion by doing these stop motion diagrams. So when a car takes off from being stopped, or a cheetah takes off, if we analyze the motion, the distance between each of those spots gets bigger and bigger. So that green arrow is growing, and so our velocity is increasing. All right, so here's a question for you. A bicycle is moving to the left with increasing speed. Which of the following motion diagrams illustrates this motion? So let's take a vote. And if you're online, put it in the chat. All right, so how many people think it's A? Motion is increasing to the left. A. What about B? All right, what about C? Or D? Okay, that was pretty. Yes, the answer is B. It starts over on the right, moves to the left. What's happening in C? What's it doing in that one? It's slowing down. It's decelerating. All right, so. All right. Another question. The slope at a point on a position versus time graph of an object is what? So this is, we haven't talked about this yet, but hopefully you've started reading chapter 2. You should have finished chapter 1 by now, and you should be reading chapter 2. So there's also, I think, are the reading assignments available? Okay, look at those. So you should do the reading assignments. They're not strictly required, but you should do them, okay? I guess you don't have to do all the problems, but it's a good way to test your knowledge. So yeah, you should have finished chapter 1 by now. You should be reading chapter 2. And then on Monday or Tuesday, we're gonna start on chapter 3. All right, so what is the slope at a point on a position versus time graph? Let's draw one. Let me get my camera. Let's draw a position versus time graph. What does that mean, position versus time? And I brought a card today so I'll make it better. So I'll make my position versus time graph. Let me stop sharing this. All right, so here's my card. And I'm going to make my position versus time graph. Okay, so on the bottom axis here, so here's the left axis, and here's the bottom axis. So we will call this, time. This axis over here, and this axis is going to be position. And we can do this for my car. So as time goes on, we're going to be moving this way along our plot here. Okay, so here's our, this axis is time. This one is position. Okay, so as I'm moving in position, let's say the first one is here, so my car is driving. It's moving this way. Okay, so we go along this way. The next one is here. And then the next one is right here. Okay, so if my position looks like this, what kind of motion is this? So here's this is position versus time over here. So this axis is time. My car is moving in a straight line, okay? So, and let's say that this is, we'll call this seconds down here. This is 1, 2, 3, 4, 5, 6, 7, 8. And then we'll call this meters. We'll make them go in pretty fast. So this will be 5, 10, 15, 20, 25, 30, and 35. Oh, and then we need 40 up there. All right. That's about, this should be 35 up here. I didn't draw my axis very good, but that's okay. We'll just make a little correction. All right. So what does the slope of this line tell me? First of all, do you know how to calculate slope? What is the slope? How would I find the slope of that line? Yeah, change in y over change in x. Now, my axis is actually x on the top and s on the bottom. But yeah, the y-axis is x, and then the x-axis is s. But you're right. Change in, and you can think another way is the slope is equal to the rise over the run. Okay, so I look at how much I go up on my y-axis here, and then how much I change this way. And so it looks like from this point right here to this point right here, I'm going to have this part right here. This will be my final position. So x final minus x initial. And then on the bottom, I'll have TF, my final time, minus my initial time. Okay, and if I can read the numbers off of my plot right here, I'll use this one right here. This is 15, so XF is going to be 15. So I'll just label this on my plot here. So this is XF, and this is also my final time. So there's my final time. There's my final position. And then this is going to be X initial, and that's my initial time. So I'll just draw those little lines there. Okay, so I can read this off then. So over here, my final time is going to be 15 minus 5, and this is in meters. So I'm going to put my units in there. And then on the bottom, my final time is going to be 2. So that'll be 2 seconds minus 1 second. Oh, so I think I'm going pretty fast. So that's going to be 10 meters per 1 second. So 10 meters per second. What is that? What units is that? Yeah, it's velocity. Okay, so this tells me my velocity. So if I take the slope of position versus time, that's going to give me my velocity. Okay, so let's do another one since we're making these plots. Yes. So let's do one other trick before we move on. Let's find the area under the curve here. Have you guys ever done that? Okay, so what is the area equal to underneath my curve right here? So from right there, so this little structure right here, what is that area under the curve? Because that looks like I've got a square down here, right? And then I've got a triangle up here. So what is my total area under the curve going to be? Well, let's take a look here. The first one, this has a height of 5 right here, and it's 1. So the area of this square is 5. Okay, so I multiply that together. So that's going to be so I'll have, well, let's figure out the rest of the area first. All right, and then what's the area of this part here? So the bottom part here that's equal to 1. The top part here is equal to 10, but this is half of a rectangle here. So this would be Okay, so this whole thing here would be equal to 10. So then the area under here is also going to be 5. Okay, so this will be 5 meters. And this is also 5 meters. Okay. Well, anyways, let's look at velocity. Okay. So let's draw the velocity for this actually. Okay. So if I were making a plot of the velocity during this time, what would the graph be for my velocity? So let's draw a picture here. Actually, let's draw another axis up here. So now I'm going to draw velocity versus position. And we'll have the same units here. We'll have 1, 2, 3. And then my velocity will go, this will be 5 meters per second, and this will be 10 meters per second. So this is meters per second, and then down here is seconds, okay? So for this time interval here between 1 and 2, what would the plot for my velocity look like? Yes. Yes. So I heard horizontal and straight line. Yes. So 10 meters per second. So from right here to here and continuing on, it's just going to be a straight line that's equal to 10 meters per second. And so that means it's constant. Okay. Now, so this is my plot of velocity. Okay, so 10 meters per second. And if I find the area under this curve, okay, so this one, if I look at it, it's 10 here times 1 second. Okay, so if I multiply that, so 10 meters per second times 1 second, that tells me 10 meters. What distance is that? So that's the distance that I traveled in 1 second. Okay? So if you have a velocity versus time graph, then you can find the distance that you traveled by finding the area underneath this curve right here. Okay? So that is the distance traveled during that time period. Okay? So this is just a little bit of practice for drawing these types of plots, but we're going to do more of these. And I think this is also on your homework. All right, so let's go on a little bit in the chapter. Well, actually, let's take a break now, and we'll do something else. Not an actual break. We'll take a break at 11:50. But let's go back to the example of our T-Rex. All right. So so how big? Does anybody know how big a T-Rex was? All right, let's look up. Let's use the Google. Yeah. Size of a T-Rex. All right, so a T-Rex is obviously much smaller than Godzilla. Okay, so a T-Rex is maybe, I guess, 20 feet long. Okay, so much smaller than Godzilla. Okay, so what's our scaling factor going to be? So, all right. So for now, let's go into groups, and I want you to do the same calculation that you did for Godzilla, but do it for a T-Rex. Okay, figure out how many pounds of meat would a T-Rex eat. Okay, but this time I want you to, instead of an iguana, because An iguana is a vegetarian, right? They just eat lettuce and they don't really eat anything else. Let's use a Komodo dragon or another meat-eating lizard as your model. So maybe use a Komodo dragon, okay? So figure out how much a Komodo dragon eats every day. We'll have to look it up. And then calculate make your prediction about how much meat a T-Rex would eat every day, and then compare it to what we know about. You can use Google to actually look up that information, okay? So work with your partners again. If you're far away from your partner, scoot together. And let's figure out how much a T-Rex must have eaten. Oh, and we can also, it says here that the mass of a T-Rex was 9,000 to 18,000 pounds. So we can test our model. Let's see if our model is any good, okay? So use the scaling factor like we did before, and let's see if we get within that reasonable range of what it says on the internet. And Monica and Neil, are you guys still there? All right, I'm gonna put you guys into a breakout room, and I will join your. Actually, I guess we don't need to be in a. Yes, all right, I'll put you to breakout room. Oh, so it says here that they can get to 3 meters long, and they can weigh up to 150 pounds or 70 kilograms. Oh, that's a much better model than an iguana. Yes. How much it weighs and also how much. Yeah, we want to test our model. So we have a known value, and so yeah. So I mean, if we start with the Komodo dragon, we have paleontologists have a pretty good idea of what a T-Rex probably weighed, and so we're seeing if our model fits within the known parameters. So this is we're testing our model of what a larger animal would look like. And really, if a Komodo dragon is 3 meters and a T-Rex is only 6 meters, that's not a huge scaling factor. So that means that the T-Rex was really only bigger than a Komodo dragon by a scaling factor of 2. So if our model is true, then this can really tell us if it's a good model or not. Okay? But if there's some kind of deviation, then maybe we need to make an adjustment to our model. Because when paleontologists and everything find the bones from a T-Rex, they have to do a calculation. All right, well, based on how big its skeleton is, how much muscle would a T-Rex have to have, and therefore how much would the T-Rex had to have weighed? And then they can get an idea of how much did the T-Rex have to actually eat. Okay, so, and of course, as I know nothing about paleontology, we're just blindly making a guess based off of math. And so let's see how close we get to what the paleontologists think. And I'm sure that the paleontologists have much better models than this, but this is basically what they do. So if you're studying an organism that is extinct, no longer exists, this is the kind of thing you have to do. You'd have to collect evidence. So you'd have to say, all right, how big was its footprint? Have we ever found a fossil with remnants in its stomach? Sometimes they find dinosaurs that have partially digested things in the stomach, and so we know what that dinosaur ate, at least partly. Or sometimes they died while they were eating another dinosaur, and then we can say, okay, well, they were obviously eating this other kind of dinosaur. So what did you guys get for the mass of the T-Rex in your model? Oh, okay. So our scaling factor is off. That means that our model is maybe not the best. So we were just basing this off of the we're basing this off of a Komodo dragon. So maybe a Komodo, yeah.
Scaling factor was pretty accurate on spaces day, but it wasn't very accurate for mass.
So, oh, okay. So how much did you find that, how much did they eat a day?
So my calculation, I got 122.4 kilograms per day.
Uh-huh.
When I looked it up, it said about 104 kilograms. So it was pretty accurate.
But not with the actual mass of, Okay. Well, so then maybe we need to find a better model for a T-Rex. Maybe let's try a chicken. Let's see if a chicken is a better model for T-Rex in terms of size. But that's interesting that we were close to the food. Because I guess, well, let's look at a picture of a Komodo dragon. Okay, so maybe one problem with our size model is that Komodo dragons are really kind of they're kind of long and narrow, and a T-Rex is more like kind of stockier, you know, like it's got more meat than a Komodo dragon. So yeah, maybe a chicken. Well, anyways, we did the Komodo dragon. That's probably good enough for now. So why don't we take a break for about 10 minutes? Go get some food and walk around or do whatever you need to do. And let's meet back here at about 12 o'clock. All right. Well, while you were gone, I tried several different models for a T-Rex, and I realized that initially what I was looking at was the height of a T-Rex. So a T-Rex was actually 20 feet tall, but it was 40 feet long. So it had a big tail. And actually, I tried it with a chicken. So I tried to use a chicken as my model, but I came to the conclusion that chickens don't have tails, and so that made a big difference. And so I tried I tried to use the actual length of a T-Rex, which is 12 meters. And if I use that for the scaling factor, then I got a mass of 21,000 pounds, which is close to the range. So that I think for a T-Rex, it said the biggest one they think is 18,000 pounds. So that's pretty close. And you found that you were even with the height, you were within. Can you try and do your calculation for how much they ate with 21,000 pounds and see what you get? So we weren't too far away from what scientists actually think that the T-Rex probably ate. Now, probably one of the issues with our model is because we're saying that we have density of a Komodo dragon is equal to the density of our T-Rex. Right? And then this is equal to the mass of the Komodo divided by its volume, which we said is the volume of a cylinder, r squared over h. And this is equal to the mass of the T-Rex. So let me know when you get it. I'm curious. And then we said, and then we had a scaling factor here for it's the radius, and another scaling factor here for its height. Yeah. And what did it actually eat? Okay. So maybe the first thing was actually better. Okay. So let's take a look at our model here and think about how could we improve modeling a T-Rex, okay? Because in our simple approximation here, we're saying that a T-Rex looks like a cylinder. Did a T-Rex actually look like a cylinder? No. And what if the width actually scaled a little bit differently than the length? So if we're saying, all right, our Komodo dragon obviously is much differently shaped, so maybe we need a different scaling factor for the different dimensions, so the radius and the height. Maybe they didn't scale the same way. I mean, we could look at the bones of a Komodo dragon. We could look at the bones of a T-Rex, and we could compare them, and we could try and come up with a more accurate scaling function for that. So maybe based off of their skeleton, if we had an actual T-Rex skeleton, then we could scale that to a known organism. Okay, so we could also use a bunch of different lizards and see what they eat. We could try it with, we could use it with chickens too. And we could try different birds and things like that. But I think this is one way, if you were a biologist, that you could go about trying to study dinosaurs or other kinds of organisms. You could basically build a mathematical model off of known organisms and then use it to predict what other organisms would do. Because sometimes you don't always know what an organism, how much they eat, until you actually study them. So if you were thinking about maybe deep sea creatures, or creatures that are very rare, sometimes there might not always be information about, well, how much does this organism eat? Maybe nobody studied it before. So, but this is an example of how you could study biology. And maybe you could use a better model. What the physicist in my department does is he actually gets a plastic whale, so they'll take a small replica of it, and he will scan that into a computer using a 3D scanner. And so based off of that, then he uses that in his computer models. So you couldn't obviously scan a blue whale, but people have made pretty accurate toys based off of real life things. So, but this is one way we could use physics and math and biology. So hopefully what you'll take away is that physics is not totally useful and that it could help you as biologists. All right, so let's go back to, all right, so we talked about this. What is the slope at a point on a position versus time graph? What is that? Is it the object's speed at that point? The object's average velocity at that point? An object's instantaneous velocity at that point? Or object's acceleration or the distance? All right, how many people think it's A, the object's speed at that point? What about B, the object's average velocity? Or C, the object's instantaneous velocity? Yeah, so it's probably C, because if you take a slope at a particular point, that's what the object is doing at that particular point. Okay, so that's the instantaneous velocity. If you only know the starting and the ending positions, then if you find the velocity off of that information, that's going to be the average. All right, so what's the example of uniform motion? A car going around a circular track at a constant speed. B, a person at rest starts running in a straight line in a fixed direction. Or C, a ball dropped from the top of a building. Or D, a hockey puck sliding in a straight line at a constant speed. What do you think? Is it A, car going around a circular track? And if you're online, please put your answers in the chat. Can you guys hear me online? Type your message in the chat. Okay, yes, they can hear me. All right. Is it B, a person at rest starts running in a straight line in a fixed direction? What about C, a ball dropped with probability? Or D, hockey puck sliding? Yes. Why is D uniform motion? Yeah. Yes, it's going in a straight line. There's no acceleration. And according to Sir Isaac Newton, if there was an infinite track, it would just go on in a straight line forever. If you throw a ball in space, it would just continue in a straight line forever. There's nothing that would stop it. It's not like on Star Wars. Have you guys seen Star Wars? Have you ever noticed how as soon as they turn off the engines, their spaceships slow down? Yeah, that wouldn't happen. So if you're going at light speed and you turn off the engines, well, not light speed, because nothing can go at light speed. But if you're going fast and you turn off the engines, you'll just keep going at that same speed forever. You will never stop unless you hit something or you slow down. Okay? So that's if you were trying to get to another planet, okay, you have to take enough fuel to get going fast enough, but you have to take the same amount of fuel to slow down. So if you're going really fast on a rocket to Mars, you'll just go right by it unless you have rocket fuel to slow down. So, but uniform motion is after you accelerate, you just continue on in a straight line forever at a constant speed. All right. The area under velocity versus time graph of an object is what? Okay, raise your hand. I'm just going to read it once. The object's speed at that point. If you think it's A, raise your hand. Is it B, the object's acceleration at that point? Okay, so we have 1B, good. C, the distance traveled by the object. This is the area under velocity versus time graph. Or D, the displacement of the object. Or E, the topic was not covered in this chapter. Okay, we had some votes for D. Why don't you guys talk about it? Talk to your neighbor. Convince them that you're right. Do you guys in the second row want to sit closer together? Because I feel like you guys are too far away to talk to each other. Since I want everybody to talk to each other, please move closer together. I like to make people talk to each other, and I apologize if that makes you uncomfortable. But talk, yes. 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 No, I think it's all, like, even if the velocity were changing, if you found the area under the curve, that would be the distance traveled. Yes, it is. Yes. So, yeah, displacement of the object is the distance covered. Yeah. Well, no, actually, no. Distance traveled by the object is different than the displacement of the object. So the displacement is where it's basically a vector from the origin to wherever the thing is. I think it's the oh no, it's just, oh, see. Did I said displacement of the object before? Okay. No, it's the displacement of the object. So that could tell you where the object was. Yes, do you have a question? So this is the velocity versus time graph of an object. So if we drew the graph, so this would be this would be up here. So this is so this is my velocity versus time. Okay, so this would be so if I were to find the area under this, then that would basically be how far the object has moved in that time. Well, so I don't like to talk about calculus because it kind of freaks some people out. Although calculus is really fun, but when you find the area under this curve, that's what calculus is basically. So when you find the area under the curve, you're taking the antiderivative of it. But we don't, I don't worry about that. The point is those are just calculus words. But what it means is if you find the area under that curve, that's just how far it's moved. Okay, that's all that it means. Because, Sir Isaac Newton, he invented modern physics as we know it, and he also invented this branch of mathematics called calculus. And calculus isn't scary, but it just talks about, well, how do things change over time? And so it tells us, well, if I'm traveling at this constant velocity, if I find the area under the curve, that's how far I've traveled, right? But we're not going to talk about calculus directly in here. It's not part of the course, but if you have a question, I'm happy to tell you about it. But practically what it means is if I'm going 10 meters per second for 1 second, then I know that I will have traveled 10 meters. So every second I go 10 meters per second. So if I traveled for 5 seconds at 10 meters per second, so here's my velocity. So if I'm moving at 10, oh, there we go. If I'm moving at 10 meters per second, and I do that for 5 seconds, so I'd say, all right, 1, 2, 3, 4, 5. Okay, then the area under here, that's going to give me 50 meters. But that also comes from the equation of x equals v times t. Okay? So if you want to know how long is it going to take you to get somewhere, this is the equation you use. So I know, all right, if my distance is, let's say, 300 miles, okay, so if I need to drive 300 miles, so you want to go to Kansas City. How far away is Kansas City? Is it 300 or 240 miles an hour? 240. Is it 300? Okay, so if I want to go to Kansas City is 300 miles away, and I can only drive 60 miles an hour. How long is it going to take me to get to Kansas City? Because it's a straight line pretty much to Kansas City, right? So I'd say, all right, it's 300 miles. I divide that by 60, so that's going to equal 5 hours. So it takes 5 hours to go to Kansas City. So let's do an area under the curve plot for that. All right, so here's Missouri. Here's my, does that look like Missouri? There it is, the show me state. And I'm driving here from St. Louis to Kansas City. There's the arch. There's the arch. And then Kansas City's over here. We'll just draw Kansas City. It's a dot. Okay. Oh, there's a bridge in Kansas City. I've been there. Okay, there's a bridge. All right. So if I go here, it's 300 miles. Okay. Then my velocity is going to be 60 miles per hour. Okay. And so here's 1 hour, 2 hours, 3 hours, 4 hours, 5 hours. I travel at a constant velocity. I don't even stop to get a snack. Although I get a lot of snacks. All right, so 1, 2, 3, 4, 5 hours. Okay, so if I find the area under the curve here, so there's my area. So I've got 5 times 60, so that's going to be 60 miles per hour times 5 hours. My hours cancel, and that's going to give me 300 miles, which just comes from the expression x equals v times t. Okay, so this is distance equals velocity times time. And this, yes, it does come from calculus. So, and when you do this, you're finding the antiderivative of this function. So that's how the calculus works. Okay, but let's go on. All right. All right. If an object is speeding up, so I step on the gas, my car, then my acceleration is A, positive. My acceleration is B, negative. So acceleration is a vector. Or C, its acceleration can be positive or negative depending on the direction of motion. So the correct answer is B, its acceleration can be positive or negative depending on the direction of motion. All right, so if it's speeding up, let's say here's my car. Okay, I'm going to wind it back up. So my car is accelerating. Okay, so it's going this way, and so its velocity is positive, and so its acceleration is also positive. But let's say that my positive axis is going this way, and now my car is going that way. Its velocity is going to be in that direction, so it's going to have a negative velocity. Its displacement vector will also be negative. And since the velocity is increasing that way, so it's becoming more negative, then its acceleration is in the negative direction. Right? So the acceleration just tells you which way is the velocity changing it. All right, so let's do draw a coordinate system here. Oh wait, I'll do it on piece of paper. All right, so here's my car. And let's say this is 0, 1, 2, 3, 4. And we'll call this way positive, so this will be 1, 2, 3, 4. And then over here, this is zeros right here. This is -1, -2, -3, and -4. All right, so look at my car and tell me if my car is going this way, which way is its velocity, negative or positive? If it's going like that, it's negative. And then if it's going this way, which way is its acceleration, negative or positive? If it was speeding up, it's also negative, right? And then what if it's going this way, but it slows down? Which way is the acceleration? It's negative, right? Because the acceleration is this way. So if you're slowing down, it's in the opposite direction of your motion. And if you want to understand what that means, if you're driving your car, go someplace safe and step on the brakes really hard. And then you'll feel that negative acceleration. So it's going behind you. It's opposing your motion. And so you'll feel the seatbelt pressing against you, hopefully, right? And that seatbelt is force, right? So we haven't talked about force yet, but if there is acceleration, then there's some force because we know that, hopefully we know that F equals ma. Force equals mass times acceleration. So if you're going this way and you hit a brick wall, which way is your acceleration going to be when you hit the brick wall? So it'll be positive or negative. So I'm driving this way and boom, I hit a brick wall. Which way is my acceleration going? Yes. Yes, it will be positive. So it'll be behind you, right? Because remember, let's say your car drives off of a cliff. So here's my car. All right. So when the car, as it was going off of the cliff, as soon as it left the table, which way was the acceleration? So we're thinking in 2 dimensions now. So after it left the table, which way was its acceleration? Yeah, the acceleration is going downwards. Now, when the car hit the floor, which way was the acceleration going during the collision? Yes, it was going up. Yeah, it's going up because it was slowing down this way, and so there was an accelerating force the other direction. So remember, when you fall off a cliff, it's not the fall that kills you, it's the stop at the end. So words to think about. Okay. All right. All right, enough questions. All right, too many questions. All right. Representing position. So we'll use an x-axis to analyze horizontal motion, and we'll use a y-axis to analyze vertical motion. We'll say if it's to the right, then it's positive. So up here, this way is going to be positive. And if it's to the left, this way is going to be negative. Similarly, with a vertical axis, if it's above 0, then y is positive. And if it's below 0, y is negative. This is the convention that we use. We always use a right-hand coordinate system. So that's our convention. Okay. So here's a motion diagram. We've got, it looks like position versus time. So our position is changing at not the same rate. Right? Over here, the position is changing a lot in a small amount of time. And then over here, it's not changing a lot. The position stays the same in time. And then over here, we see a big change in position again. And we can represent that same motion another way. So here, the change in position is represented by these arrows. Okay, so from one point to another, there's a big change in position, so there's a big arrow. And then as we get over here, there's a small change, so it's not moving very much. And then it speeds up over here again. Right, so in this point, if we take the change in position versus time, that gives us our velocity. So from here to over here, it has a high velocity. And then over here, it's a slower velocity. All right, we can make a recording of each of those positions versus time. So we'll say this column is our time. So at 0, we're at 0. And then over here, so each of those points we can put into a table, and we can plot this in Excel. And we can see between 2 and 3, it changes by 60. So there's a 60-meter change. But over here between 3 and 4, it only changes by 20. Same thing here. It's only a 20 change. But then as we go from time 6 minutes to 7 minutes, there's a change of 100 meters. So there's a big change there. So our object is accelerating. It's going much faster after 7 minutes.
Dr. Wisby.
Okay.
I can't see
So in our position versus time graph, if we take the slope of that plot, it gives us velocity. So rise over run, okay? Delta x over delta t. So I would say, all right, I don't want to do the whole graph. If I just said, all right, give me my first position here at 0, and then I said, all right, I'm going to find a position over here, I'm going to ignore all this stuff in between. I'm not going to care about what's going on right here. What would that tell me if I just took a point at the very beginning and one at the very end? What kind of velocity is that? Yes, it's the average velocity. And the average velocity is just, what is my average speed over this whole time period? Like, for example, if you drive to school every day, okay? You think, all right, what speed did you drive? So how fast did you drive to school? Did any of you drive? Well, nobody drove? Okay. Well, I was on the freeway and I was going about 65 miles an hour, but I also hit some traffic lights. And I was sitting there going 0 for a long time, okay? So if I think about my average velocity, then my average velocity for that whole trip was probably more like maybe 30 miles an hour. So I had times where I was going much faster, and then there were times where I was going very slow. And all that stuff in between, I didn't really care about. But so my average velocity over that whole time was maybe 30 miles an hour. Now my instantaneous velocity changed dramatically, and that's what your speedometer tells you. That's your instantaneous velocity. Okay, but for each of these areas, okay, so let's say this part was where I was driving down the street, and then here I was sending a tweet. Oh no, wait, I don't actually send tweets while I drive. Yes. Oh. Oh man. I'm not sharing my screen. Oh, Monica, guys, I'm so sorry. There we go. Okay. So here we go. All right. So my average velocity is if I took a point at the beginning and at the end, but then each of these different areas I could find the slope of those each area. Okay. So I apologize. I guess it's just oldness. Sometimes I don't always work Zoom right. All right. So we can, actually, let's skip ahead. All right. So let's look at this problem. This one's better. Okay. So here is a motion diagram of a car moving along in a straight line on the road. Which velocity versus time graph matches the motion of the diagram? So let's take a vote. Raise your hands if you think it's A. All right, what about B? Or C? Got some C's, all right? Or D? All right, so we saw a lot of C's. Why don't you guys talk about it and decide which one you think it is? All right, Monica, which one do you think it is? Are you still there, Monica?
Yeah, I think it's C.
C? Okay. All right, so why do you guys think it's C? Somebody tell me. Well, it looks like here, the arrows are the same height, or same length, and they're about the same. So we've got a constant velocity here, but then over here, they get much bigger. So this one has 2 steps. We go from a smaller velocity to a bigger velocity. So yes, the answer is C. All right, here's another one. What is the velocity for this one? Okay, this is a little bit different. Now it's going to the left. How many people think it is A? Or what about B? Or what about C? Maybe C. Okay, what about D? Okay, and then E. All right, it looks like the D's have it. Why do you think it's D? Somebody tell me. Well, we know that this thing is moving to the left, so it's going to have a negative velocity. And at time t equals 0, that's actually over here. So on our plot, it's actually going to be backwards. So t equals 0 is right here. And at the beginning, we have a small change in position. So that corresponds to a slower negative velocity. And then it continues in the same direction. So it's still going negative, but now our velocity increases. And so it becomes more negative. So it goes from the smaller negative velocity to a more negative velocity. All right. So a graph of position versus time for a basketball player moving down the court appears as follows. Okay, so here's his position. Then all of a sudden his position starts changing. All right, so it's as time goes on, it's becoming, it looks like, well, I won't say it. All right, so which of the following? Is it A, his velocity versus time? B, C, all right, or D? All right, I think the C's have it. So at first it's 0 because his position doesn't change. Then it becomes more negative, so he has a negative velocity. And so C is the only one where that looks correct. These other ones, what does this mean if you have a slope in your velocity? What kind of motion is that? What's happening during that if your velocity is changing? That's acceleration, right? So if the velocity was changing, that would be an acceleration, but he's running at a constant speed. He's got a slope here, and so it's C. Okay, finding a car's velocity from its position graph. All right, the graph gives the position versus time of the car's graph. Draw the car's velocity versus time graph. All right, so we'll use the steps from 2.1, but let's look at the beginning. All right, in the beginning, his position is becoming more negative. So try and draw this one out. Make a drawing, and you can turn this in on your Komodo Dragon T-Rex calculations. So put a drawing on the back or somewhere on the sheet, wherever, and talk to your partner, make a velocity diagram. All right. I think that's probably enough about velocity. So you can turn your drawings in at the end, and then we'll. Let's go on now to acceleration. Okay. All right. Let's talk about uniform motion because we want to get to hopefully acceleration today. And there's a lot of slides, so we're not gonna, can't possibly do them all. But if something is in uniform motion, then that means it continues on in a straight line. There's zero acceleration. So the motion capture for this would be every arrow would be the same length and there would be no acceleration. There'd be in our position versus time graph, we would get a nice straight line and we could calculate the slope anywhere along this line and that would give us our velocity. So no changes. So here's the general formula to calculate our velocity. This is going to be an important one. So you should definitely write this down, internalize what it means. You'll see this on the homework and probably tests. Okay, so from this formula here, we have our Vx. Okay, so we have our velocity. If it's not changing, our velocity does not change, then times time equals or plus our initial position gives us our final position. So if we don't start at the origin, okay, then our initial position won't be 0, okay? This initial position tells us where we started. Then delta t is how long did it take to take that trip, okay? So delta t is our change in time, and then xf, of course, is our final position, okay? So this is one of those equations you should know, put it on your sheet. And then up here, of course, rise versus run. This comes from the plot of displacement versus time, right? So this is for if you have a projectile. So if I launch my car here, let's drive my car off the cliff again. Okay. So during this whole trip, once my car accelerates, its forward velocity never changes, even after it goes off the cliff. At the end, it stops, but so your forward position, your forward velocity never changes, right? So yes, physics is populated with equations, but here are a few of the most basic forms. Okay, so we have our y equals 4x squared, okay? And we see this in many different kinds of equations for kinetic energy, potential energy. This comes up a lot, okay? And these graphs have the same overall appearance, and the expressions relate different physical phenomena, but all three have the same mathematical relationship. Because it's important to think about all the equations that we do in physics, they mean something in the real world. Every equation you can think of as an experiment, all right? It's not just mathematicians, they don't like it when sometimes they don't like it when you apply their equations to actual things. But in physics, I like to think of each equation corresponding to an experiment. I could go into my lab and I could measure this, and then I could write an equation that would tell me what's going to happen when I do the experiment, right? That's how we define, I guess, something as being real, right? Is we can come up with a mathematical relationship. For some reason, our universe, as we know it, follows the laws of mathematics. Things don't just happen randomly, like this expression here. This is the amount of energy that something has, okay? And if my car has a certain amount of energy, that energy can never be destroyed. So even though when I drive it off the cliff here, it's got some kinetic energy, and now it does not have kinetic energy, but the energy that it did have went somewhere. Part of it went into heating up the car, part of it went to making a sound, but that energy is always here. It never disappears, okay? And we'll use this type of relationship a lot, and it looks like this. This is a parabola, okay? So this is a proportional relationship. So there's some constant, sort of like our scaling factor, okay? Like we did with how much would our T-Rex eat, right? We had some scaling factor here, C, and so we said, all right, if my iguana eats this much meat, then according to my scaling factor, the T-Rex must eat this much meat. All right, so that's a relationship. Now, maybe our scaling factor was a little bit off, okay? Maybe a Komodo dragon or a chicken is not a good model for a T-Rex, but if we were paleontologists, we could come up with a better scaling factor. So this is true in physics, but it's also true in biology, okay? So, and these relationships probably dominate biology also, just like in physics, see? Okay. All right, so our scaling factor here, it's a proportional relationship. So if x has the initial x1, then y has the initial y1. Okay, so if I start off here, my initial position, then I can get to another position on my plot here by doubling this. Okay, so I'd say, all right, this will tell me my next factor. So as x increases, then I get the y relationship. So when you look at a plot, this axis is the variable that you control, right? And that determines what this is going to be. Okay, so this is your dependent variable, and this is your independent variable, I think. Yeah, I probably said it back. Okay. All right. Here's a position graph of an object at 1.5 seconds. What is the object's velocity going to be? So let's look at our plot here. So 1.5 seconds, that's here between the 1 and the 2. So I'd look right here and I'd say, okay, this is position versus time. So that means I need to find, that means I need to find the slope of the line right here, okay? So I'd say, all right, well, let's look at this. My rise is about 20 meters in 1 second. So, because it goes from 0 to 20, and that took me 1 second. So I think my velocity is gonna be 20 meters per second, okay? And yes, so at t equals 1.5 seconds, I look at my plot, I find the slope, and that's my velocity. So, all right, that's all for today. Give me your papers, and thank you for coming to class today. All right, thank you. Thank you. Oh.
I wasn't sure since I know I emailed you about the calendar.
Oh yeah, sorry about that. I need to get the calendar working.
Because I was talking to some other people, they said they couldn't get it to work either, so I didn't know if you could just.
No, I think I need to I need to adjust the setting. Is the university open on Monday? I totally forgot about that.
I wasn't sure, so I was just gonna ask.
I'll send out an email about that because I actually don't know. I think we don't have class, but let me double check on that.
Sounds great.
All right.
Thank you.
You too. Thanks.